what's been really interesting to me in my conversations with Zackery from the beginning is that he reflects on acoustics through some really unexpected mediums like writing and design and visualization. And he pulls from his background in physics and architecture to essentially open up new frameworks for understanding that ultimately establish the principles that you find in his essay, Acoustic Ornament. And I've been playing this game with this book where I just open it up to a random page and imagine that what I'm reading is in a totally different context, like love or tragedy or magic. And it kind of works like a novel almost every time. Like any single line can kind of feel like a strange metaphor for life. So I'll be curious if any of you have that experience with the book. But I think it's really a very artful and unique approach to something that's like can be a very highly technical topic. I think that was all I wanted to say. But anyway, we're going to have a little bit of a discussion after Zackery's talk, and maybe you can have a little bit more time to roam the museum. And then if folks are interested, we can head down the street for a little bit more of like a social, since the museum has to close at 7 o'clock. So.
This is the first time that I'm giving this talk. Every time I do something like this, it's a chance to push the work ahead a little. But maybe a little bit more about the background. I did study physics pretty intensely up through a master's degree in gravitation. And that was a crazy experience in a lot of ways in that the way that math can model our world was really surprising to me and beautiful. I then spent 8 or 9 years pretty immersed here in Chicago. I'm in Detroit now, but here in Chicago in a firm called Kierkegaard Associates doing acoustics consulting. And unlike physics, that was really challenging and interesting in other ways. Getting a building made is a real challenge. You have time constraints, site constraints, budget constraints. There are all of these things that arose that really weren't there in physics. And I started to get a little bit frustrated, not in the state of acoustics, but in this disconnect between the experts in acoustics and the design community. The experts in acoustics are excellent. There's a lot of hardworking and intelligent people in that world, and they are there if you need them. But I was continually disappointed at, I think, a lack of an intuitive understanding in the design community of what we're doing. And I put that on us, honestly. If we're the experts in acoustics, we need to be able to talk about what we do in ways that are really useful to those who make a lot of the decisions about our built environment. So in around 2011, I left Chicago. I went to upstate New York. I followed a building I'd worked on there called MPAC, the Experimental Media and Performing Arts Center by Grimshaw Architects. And I stayed there for about 5 years, and I just started thinking differently about this. I started asking some difficult questions. And over the last decade, this essay is really the thing that came out of that. It's 6,000 words. It's very, I think it's very simple and readable, which was hard to do. But to me, that was how those ideas came together. And this is the first time I'm having a chance to really give a talk on this. So this is really the lecture version of this. There are some things we can do that you can't do in a book, like watch visualizations. So I'll be asking Jessica to forward these. To start, I want you to imagine that there's nothing around, no built environment of any kind. It might look like this next slide, just say a black field. And there's air, though. There's just no surfaces around you. And I want you to imagine clapping your hands a single time. Go ahead and play. Clapping your hands is kind of fascinating. We're surrounded by the air, of course. Air molecules flying everywhere pretty randomly. There's a lot of energy in it. When you clap your hands, of course, if you move your hands together kind of slowly, the air just moves out of the way. If you do it fast enough, you create a pulse. It might look something like this. And that pulse then expands outward. And it turns out that the reason, I never asked, like, why does sound expand outward? One way you can look at it is that when you clap your hands, you're giving something that has very little order, you're giving it order, you're giving it structure. And then it can do any almost infinite number of things with that structure. And it turns out that nearly all of them involve becoming less structured. So it's really just this chance occurrence over and over again that it just happens to go outward. The chances that it would go inward are so low that it just never happens. So it's this increase in entropy. It's this dissipation. And you saw this stop. This is a wave-based simulation in acoustics. It's two-dimensional. You can do them in 3D. They're incredibly time-consuming and take a lot of computing power. But the 2D version represents it pretty well. You can think of this as a field of pixels, and it's a series of images that were created by a computer program. The algorithms for this have been around for a few decades. Still not really used much in practice because even the 2D version is pretty computationally intensive. But what you're watching is a series of images. So you imagine you basically seed it with a point in the middle of high pressure, just like you would if you were clapping. And then you apply these equations to it, and it marches it forward, and then you can assemble it into a visualization. So there's not really much interesting that's happening when there's nothing around it, except that it expands outward. And I find that to be pretty interesting. And just to note that it's dissipating, that without any surfaces, without any enclosure, without anything, the sound is dissipating. The amount of energy you give it at the beginning doesn't change. It's spreading out, it's getting bigger. So sound has a tendency to dissipate no matter what we do with it. But it's more interesting if you go to the next one, which is adding a surface, and go ahead and let that one play. So now you're going to see a little bit about what happens with the wave base. This might look like a pretty defined circle, but it's actually kind of fuzzy because this is sound moving in air. So it's like air is like a fluid. And you'll see what happens when it encounters this surface. This surface is a perfectly reflecting surface. There's no absorption to it. And you'll even see when it gets down here, it'll bend around this corner a little. That's our experience with sound, is that it has a tendency to bend around things. I can't stand behind a column and expect you to not hear me. The sound just bends right around it. And that lets you, what happens here is what lets you really see the wave behavior of sound. You can actually see how it expands outward like that. So most importantly though, this expanding, dissipating wave of sound just folded. You could imagine this as a circle, and that flat surface folded it over. Let's go to the next one. More interesting if you enclose it entirely. That folding is going to happen, but now at 3 sides, and we'll speed it up a little so you can watch this. These images are about 10 meters, or they're modeling surfaces that are about 10 meters across. And again, the boundaries are perfect. I like to study perfectly reflecting boundaries because I think they illuminate a lot. Even though in the real built environment, everything has material properties. We'll get to materials in a minute. So one way to think about this expanding sound wave is that it's a big circle that has literally just been folded many, many times. It's bounded by this enclosure. It's still dissipating inside this enclosure, which is why it's filling it slowly, right? At the beginning, you saw a lot more black space. Now you see the grays and the whites moving in. The sound is actually dissipating. We haven't talked about acoustic products. We're not going to talk a lot about acoustic products. So this is just what happens to sound, even in an environment where the walls are perfectly reflecting. It is still going to find a way to dissipate. And then I think the really interesting question for architects and designers is, how might we be able to control this? What if you wanted this to dissipate more quickly or less quickly? What might we do to this boundary to get that kind of result? This one's, we'll let it finish. It keeps its symmetry. It's really, I could watch these all day. It's very beautiful. By the way, this is very slowed down, so it's slow motion. Sound moves at about 1,100 feet per second, so it does this all in a fraction of a second. It just fills the space. Okay, let's go to the next one. So this is an example of how you might slow that dissipation. And maybe that even makes intuitive sense. You have a sound wave that's expanding outward and is dissipating as it does. What if you shape the wall surfaces so that it counters that a little bit, causes it to focus a little bit? And this one, this is the same volume on the inside. It's the same area on the inside, but the walls are preventing the sound from dissipating as fast as it would otherwise. This one has kind of a sinister look too. And notice how, I mean, if you were to play this one side by side with the last one, how much empty space is still in here. So it's always the same amount of energy in that initial pulse. But the last one, the flat triangle, dissipated it much more quickly than this one did. Let's go ahead and move to the next one. What if you wanted to dissipate it what if you wanted to dissipate it more quickly than the triangle? You might do something like this. The shape of these boundaries tend to spread the sound out more quickly. And I think this one's remarkable with how fast it fills the interior space. And a beautiful thing about these simulations is that you can just do anything you want. This is a custom code that I wrote, and I draw this in Rhino, if those of you are familiar with it. I use Grasshopper to output the points. I feed it into, this is in Python now. I started in MATLAB. MATLAB's very expensive. Python is great. And I can just draw anything I want and study it. So you can look at these beautiful, simple shapes that maybe you would never actually come across in the real built environment. And look at how quickly that filled that. So I think even if this is all that you saw, knowing that the shape of a room helps determine how sound dissipates, even if the walls and the floors and the ceiling are all perfectly reflective, I think that's an important takeaway for the design community, right? And you can have you could actually, if you're going to start designing a concert hall today, you could actually make decisions on that initial form based on this. Do you want the sound to keep focusing back to one spot, or do you want it to dissipate? Let's go ahead and go on to the next one. So these are little bits that are pulled from the essay. The objects around us change the sound of the spaces that we're in. And it doesn't have to be labeled acoustic. I really have come to dislike the term acoustic when it comes to surfaces and products. Those are things that are designed to have heavy influence compared to other things. But anybody who's ever moved out of their apartment and moved all their things out know that it sounds different after you do that. The stuff that surrounds you has an effect. So putting an object in a space will change the sound of that space. And here's an example. A single chair. And you might notice that because that's no longer planar, because that's a complexity that's added, this space is actually going to dissipate sound a little faster than the last one. And I'm not saying that you'd notice a difference if somebody brought a chair into a room, but even a hard chair is a change in the sound of that space. And so you can start to imagine placing a lot of chairs, or placing chairs that were designed to, or just happen to absorb a lot of sound. Okay, let's go to the next one. I like to ask people sometimes, what's acoustic in this? You've been here long enough already that you probably guessed that it's everything. There's really nothing here that would be called acoustic. That's a lighting manufacturer that actually makes acoustic fixtures. That's not one of their acoustic ones. But those things are all influencing the sound of the room, whether it's the light fixture or the birch stalks or trunks in the corner. The person walking across, people affect sound, or clothing does. Certainly this chair, even that table, which is flat, it's a more complex thing than the floor itself is. Let's go to the next one. And this one, we knew this way back. This is Riverbank Acoustical Laboratories. You are all in Chicago. This is in Geneva, Batavia, Illinois. If you're ever looking for a nice field trip, it's just on the Metro line. This lab has been in use for more than 100 years. It was the first one in the world. I'm going to it in 2 weeks for a client. Chicago is a great place for acoustics. This is a testing chamber that we still use today. It has a reverberation time of more than 6 seconds. So that means like you drop a wrench or something, you will continue to hear that impact for a full 6 seconds. which is a ridiculously long period of time. In the 1920s, we didn't have loudspeakers, and so to create test tones to measure sound, by the way, they use this room to measure how much objects and surfaces absorb sound. Instead of that, we now have a speaker, but that was an organ to create the sounds, and we didn't have reliable microphones. They were very early at the time, so you had to be in the room listening to the decay and using a stopwatch of some kind. But your clothing influences the sound of the space, and since you have to be in there, they made this box simply to negate the effects of your clothes. So if you were to come back the next, let's say your test took more than a day and you changed your clothing, you wouldn't know whether differences were real or whether the clothing, or whether they're from your clothing or whether they're from what you're testing. I've asked if they still have this. They don't. It's lost. And I suspect that they had a bonfire or something when they finally didn't need it anymore, because it looks like a nightmare to me. Okay. And this is another image from that same laboratory from the 1960s. This is a seat test. If you're American Seating or some other company, you know that your seats will influence the sound of a room. And you probably wouldn't be building a theater of any kind if you didn't think you could put people in the seats. So you actually have to run the tests with people in place. You can see some of them are holding hearing protection because they would sit there during the tests over and over again. And when you talk large crowds, thousands of people, even the weather influences the type of clothing, which influences the effect that it has. So this is something we know. None of this, most of what this is about is not really unknown stuff. It's just putting things, I think, that we know together in a way that's useful. Let's go to the next one. This is from a book by Vern Knudsen from the 1950s, and this is all about how you set up your living room for good piano sound. And I love it because there's not a single, I don't have anything against acoustic products. I have clients who make acoustic products. But I love that this doesn't have any acoustic products in it. This is your couch, right? This is the bookshelf. This is drapes and carpet. And there's some of the things they don't call out, but this shaped stone is diffusive to sound. Okay. So this is a slight modification to, it'll change the sound of the space. I like to think of it in terms of it changing the shape of a space. So if you go to the next one, I think I go back to this. This is an image of that simulation without the chair, and this is an image of it with. And you can see how it dissipated faster on the right, and it's not a mistake that I drew the chair as a part of the enclosure, because sound really doesn't care whether this was a shaped floor or whether it's an object in the space. That can make sense. Right now, as an audience, we are taking a fairly flat concrete floor and making it way more complicated, way more complex. It is shaped in a very impressive way with all of the seats and all of the people in it. And that is maybe a semantic thing, but I think it's important because when I think about hanging an acoustic panel, a felt panel or something that's going to change the sound of a room, I think about how it's changing the shape of the room. And when it comes to felt and things, you can think about the micro scale shape. Like there's a reason that clothes are so dissipative to sound, and it's because they have this incredible complexity. If you just imagine zooming into the fibers that are involved. And so hanging an acoustic panel is taking maybe a completely flat reflective form and turning it into something that is way more complex, which has a tendency to dissipate sound more quickly. Okay, let's keep going. But let's talk about material for a second. Rightfully so, you could take a sheet of plate glass and a piece of fiberglass and say those are different materials. But what bothers me about that is that doesn't explain why they behave differently acoustically. And if I asked you what the substance is, you'd have to admit that they're both glass. So that is, there's something going on there that you can't just say glass is a bad thing acoustically or glass absorbs sound. It depends on what configuration it's in. And this is an example of that. This is a resin panel. It's very reflective to sound. It's very flat. If you take this panel and you chop it up into a bunch of pieces and you fold them and you make a sculpture like you see in the middle, same material, it starts to diffuse sound. It starts to dissipate sound a lot more than it does in this form, same material. And it turns out that if you make felt out of that same material. This is all resin. This is a close-up so you can see the fibers. It starts to absorb a lot of sound. So it's perfectly fine to say this doesn't absorb much and that does absorb a lot, so I'm going to use enough of that in my design. But I think there's a lot of possibility when you think about how there's a really, you can imagine a continuous change of geometry. If everything affects sound and the more complicated it is, the more it dissipates, then there's a lot of design possibility there. And it isn't just resin, it isn't just fiberglass. This is ice and shaped ice and snow. So it's all frozen water. And it turns out that flat ice is very reflective to sound, shaped ice is diffusive, and snow is very absorptive to sound. And this image even shows that there's kind of a transition. You can think of a gradient between them. So material is really, I like to think of material not as whether it has acoustic properties or not, but material is the thing that makes the shape and the scales possible. So glass and resin are excellent at becoming tiny little fibers, and that's what makes them good absorbers. Concrete, not so much. It's not impossible to make it into an absorptive surface, but has a harder time with it. Wood, not as much. So when you think about material in that way, you can start to ask what materials can take a form and a scale that can give me the acoustic properties that I want. And this is the image that you may have seen. This is a single line that just goes from flat. I like to think about the continuity, the increase in complexity. This is a reflective area. This is a more diffusive area. And this is a more absorptive area. And it turns out that even if you just grab the pre-existing acoustic products, put a reflector here, a diffuser here, an absorber here, you can just see that increase in complexity as long as you're willing to look at the fine scale of the absorber. And I say complexity, it's a really generic big term, right? But one thing that is a measure of complexity is surface area. But I don't mean, so if you imagine a 4 foot by 4 foot sheet of glass, that has an area of 16 square feet. If you imagine a 4 foot by 4 foot piece of fiberglass panel, I'm not thinking of it as an area of 16 square feet. I'm thinking of it as a surface area of probably hundreds of square feet, if you really take into account the tiny fibers. And you can calculate some of these, and I've started to. So on the top, you have a flat reflector. This scale on the bottom is true surface area, I'm calling it, the one that includes the fine scales, versus the footprint of it. So if you have a flat reflector, it's essentially 1, its true surface area is equal to its footprint. And then you start to get into, these are all diffusive products, it starts to grow. If anybody's familiar with Blackbird Studios, I don't have an image, but it's a really interesting one in Nashville that has incredibly deep diffusion. It's way more surface area per square foot than typical diffusers. They do that for a lot of reasons, but notice how it jumps up. And then, yes, George Massenburg. Yeah, it's a beautiful room too. And then 10 centimeter melamine foam. Notice that this is a logarithmic scale down here. So a 1 meter square, I think I was thinking in meters here, a meter square of 10 centimeter foam has a true surface area of about 400 square meters. BASF, I think, is the company that does most of that. They've just figured out how to make an incredibly fine, porous material. And I think that this leads nicely to just thinking about how we can use materials in a lot of ways. And it also opens up other possibilities. This is a recording studio that I did in Brooklyn, and that's the back of it, and we decided to use plants instead of a typical diffuser, the back of so when we start to think about complexity, surface area, and the ability for it to dissipate, and start thinking about material as far as the form it can take, not necessarily material in any other way, just what are the possibilities of the form, then the design world opens up to all different possibilities. This is a project I did to test the acoustics of books in my apartment in Detroit. This is the Detroit Sound Conservancy's collection. They loaned it to me for it, so there's also a lot of acoustic and music books here. I did this with colleague Misha Wolf, and he and I actually measured the room with and without the books, and it's significantly more acoustically, it's significantly drier with the books. And probably none of you have ever been in a library or a bookstore that was way too reverberant. But a way of understanding this is to think about the form of this. That shouldn't be surprising. The form of this is really nice, right? As far as its complexity, you have all these different volumes, sizes, distances. They're off of the wall, so you have some good depth and this variation. And so that's not to say that that stuff can necessarily replace the acoustic products, but I think designing with that in mind is valuable. Or a wall of jeans. These are actually my jeans over 10 years. I wear them out, moving acoustic materials around, and then I hang them on the wall when I retire them. And it is pretty remarkable how much these absorb sound. Go ahead. But I wanted to make one other point. This is a conference room, I think in Omaha. I can't quite remember where I was, but maybe some of you recognize these. They're sound blocks. They're like concrete blocks with openings. And they have a really, if you're familiar with NRC, pretty high NRC. That's a 0 to 1 rating for absorption. I think these come in at 0.7 or 0.8. They absorb a lot. But I remember thinking, like, why? Okay, this is concrete, which is pretty reflective. This entire surface is like 92% or 90% concrete. It's only 10% openings. How could you possibly get something that absorbs 70% of the sound that's incident on it when 90% of it is a reflective material? And the answer is that we're looking at this with our eyes. We're looking at it in a very precise way. We are taking advantage of hundreds of nanometers in wavelength. Very tiny, very precise, allows us to resolve these details. Sound doesn't see it this way. Sound is much bigger. The sound of our voice is this big to, this big. It can't even resolve this. What sound is seeing, you could imagine taking a slice through this. There's a cavity behind there and a bunch of fiberglass in there. And then there's a cavity behind this one. And so if you imagine taking a slice through it, it's this very complicated thing. And so sound is blurry. It sees this in a way that's different. And I think sometimes our eyes are helpful, but sometimes they get in the way of understanding why something like this works. And this product has been out for, decades. I remember, I think in my grade school gym. Okay, and how are we doing on time? I think we're okay. So we've talked about a few things, and this is the part, I'm still having, sometimes a hard time putting this all together. I think in the essay it does it nicely. Speaking about it is a little bit different, but if you imagine a space, if you imagine that the shape of a space is a primary determining factor in how fast it dissipates sound, and if you imagine that the objects that we put in the space is part of its shape, not really something extra that carries something with it. It's part of the shape of that. And we think about material being the thing that determines the shape that we can make out of all of those things. Then suddenly we have a way of assessing rooms, often using our eyes, but designing for sound and assessing rooms based on our understanding of the way that shape works. And I think the next one, I think this is the way it's written. I think I'd rather, well, maybe I'll just read it. Material is substance, composing surfaces and objects, all acoustic, moments on a continuum, integrally determining the shape of enclosure, giving it form from the tiniest pore to the largest sweeping curve, the whole of which decides the quickness of the fate of sound made within. Let's go on to the next one. So wait, before you start this one, this is not going to be very exciting, by the way, but I wanted to make a point. I don't think that surface area is the end-all, be-all, but I do think that we could use a few guides that are accessible to us that, even as an expert in acoustics, it is a real bummer to have to only use stuff that's been tested out at Riverbank, because we design with so much more. We make decisions with so much more. I like doing things like testing books, but I want to understand this sometimes without testing. So when you put that all together, though, surface area is a really nice guide. And one of the things that it led to is that if greater surface area tends to dissipate sound more in a space or dissipate sound more quickly, then what could we imagine being the minimum possible surface area? And that's a mathematical thing. It's a sphere, right? For any given room, the way you could minimize the volume would be to make a sphere. And so go ahead and play this now. So guess what happens when the sound tries to dissipate in a spherical room? Right, back down to the center, and then it just keeps going. It doesn't want to. The room doesn't let it. Now, in reality, the air would slowly dissipate. You get losses at the boundary, it would happen. But if we're just speaking geometrically, this is the most interesting shape maybe, or the worst shape. It depends on what you're trying to do. But for most things, if you think about, if you imagine this being full of people, the people would dissipate sound. But if you imagine it being full of people, if you have a concentration of energy in one place, it means it's not somewhere else. So you're going to get problems. We actually want rooms that tend to distribute sound out. So this is the really core part of the essay is something I'm calling the sphericity conjecture, which is that the further a room's shape deviates from a sphere, the more quickly it will dissipate sound within. And I'm calling it a conjecture on purpose because there's a lot of work to do to prove something like that or to find the right formulation of it. But I've been in thousands of rooms. I've listened to them. This tends to work. It really does. Can you go to the next one? We're not going to make you watch the whole thing. It would actually, eventually the calculations start to, you might have saw some error effects showing up, like the calculations start to go off the rails. Does anyone recognize this room? The Maparium in Boston. Put it on your list if you're ever there. This is the spherical room that I know about. With the exception, of course, of this acrylic bridge that goes across. Actually, I think that's glass too. But it's entirely in glass. It's about a 30-foot diameter globe. They built it in the 1930s. It's at the Mary Baker Eddy Institute. And you can walk out and stand right in the center, and it is by far the most extreme space I have ever been in the sense that if you stand in the middle and make any sound, it seems to come back at you tenfold. And if you're right next to the person doing that, you can't hear them at all. It's pretty remarkable. So this idea of surface area, though, at one end, you get rooms like this, which are neat, but almost novelties acoustically. They're not very useful. It's just very cool to experience. If you go the other end of the spectrum, how far can you get away from the sphere would be the next. And this is an example of that, an anechoic chamber. If you imagine the surface area involved in this with these deep wedges, this is at Bell Labs, and this is not a visually reflective floor. He's standing on a wire mesh, and there's those wedges are below it too. I think back then they made these usually out of fiberglass. They often do them out of foam now. And what happens in a room like this? Anechoic, no echoes, literally nothing. You get nothing back. So from one room that has a very strong response to a room that you get nothing. And these are great too. If you ever get a chance, like the map, put the Maparium, Riverbank Labs, and one of these rooms on your list, because especially if you design buildings, it's kind of neat to experience the two extremes, and then you know that you can design to anywhere between those two things. And I just wanted to give a nod to this equation. The lab at Riverbank was built for Wallace Sabin, who was really the one who started all of this, acoustics. He made this equation in the 1890s, and it's called the Sabin equation. And very simply, to calculate reverberation time t, how long it takes for sound to decay, you need some constants, which is the k value. You need things like the speed of sound. I think temperature plays into it. There's a few things. But the volume of the room, and then the surface area times how absorptive the surfaces are. And we use this equation just about every day. I use it just about every day. It's really useful. But what I think is remarkable is that if you ask what did designers have control over in this equation, the K you don't, because you can change it in minor ways by changing humidity and temperature, but generally speaking, rooms all behave the same. So you're left with this V over S times A. So the volume of the room and the surfaces and their acoustic properties. Where A, I'm sorry, it's actually alpha. It's a measure of how absorptive something is. So we have volume over area times the absorptive properties of the surfaces. This actually acts a lot like sphericity. If you get rid of this alpha, you kind of absorb it into, no pun intended, absorb it into the surface area here. And instead of having to take it to the lab to find alpha, you just say, I'm going to consider all of the scales that matter, the tiny fibers and pores. You suddenly have V over true surface area. That's sphericity. A spherical shape will minimize that, and a shape like an anechoic chamber will maximize that. I'm not claiming anything other than this seems to track in the same way, and I think it's a useful thing to use in design. In other words, if you want to dissipate sound more quickly, add complexity. If you don't have to know the effect of it, add a wall of books. Know that it's going to push the room in the right direction for human communication. And if you need to predict something exactly, we do have ways of doing that, but we can start designing a lot more intuitively. Okay? And yeah, we're actually doing pretty well on time. I have a couple more things to show. I think the more exciting thing since the essay's been written has been trying to implement it, trying to do something in practice. That's Katie Newell. She's a brilliant architect who is currently at the University of Michigan. With her and Wes McGee, who is also at the University of Michigan, we've been experimenting with how we might access these different areas intentionally, these different areas of acoustic behavior intentionally with the modification of glass. So Katie uses this little kiln, and you can put pieces of glass in the kiln and heat it up, and then they sag. And this is a wall surface. We're calling it long range. It doesn't do anything except demonstrate these ideas. If you go to the next one. On this end, you have flat planes of glass. And then as you move to the right, you get increasing depth and increasing complexity. And we also did 2 layers of glass. So there's another layer on the back side, so that as this went, the slumps, the glass could get more severe and create pockets on the inside, which also adds surface area. And you can see these cuts. So these cuts start to open up and they expose areas inside. And the idea was that you would start with a reflective surface, enter diffusion or scattering of sound, enter absorption, because you can absorb sound with something called Helmholtz resonance. If you have a cavity and an opening and you do it right, it will actually start to absorb. And then you can actually transmit sound if you make it open enough. And so the idea was to do that. And in reality, I think it worked a little better than we intended, because really every part of this has all 4 of those properties: reflection, diffusion, transmission, and absorption. The reflection, diffusion, and transmission are apparent just by being in the space and by knowing that a shaped surface will tend to scatter sound versus a flat surface. But we did take it to Riverbank. I like that this is in Chicago because it's cool to talk about Riverbank. Can you go to the next? I think I have a plot here. Yeah, so this is the last of the math and the plots. Frequencies down here, so basically bass on this side and treble on this side. The range of the human voice is roughly here to here. And then on that side, we have what's called Sabins, or total absorption. So we call it a flower. If you go back, can you go back one, Jessica? We basically took a flower that didn't exist, a completely flat one. So if you imagine the 7 modules that are totally flat. And then we took this flower from this end, and then we took one from the absorptive area, and I think we took the most severe one. And so if you go back to the data, you actually see, if you forget this from this side over for a second, that progression is as you move down this surface. It's not a lot of absorption. We're trying to demonstrate that it exists. So in other words, from left to right in that image, this surface is absorbing more and more sound. it is a gradient acoustic surface. And I think remarkably enough, it's one that we didn't just decide to go make a diffuser and decide to go make an absorber. We actually took a system that started as reflective, a flat piece of glass, and the slumping process moves it through all of those areas. So it actually passes through on its way to absorptive or transmissive, it passes through. By the way, one other thing I forgot to mention, can you go back? We use something called the auxetic patterns with these. So if you cut glass in a certain way or anything in a certain way, it will move faster, I would say. Auxetics they're still something I'm trying to understand. It's a complicated field. But you know those balls that if you like pull them, they open up? Most things when you pull, they get narrower when you pull them. Auxetic systems get bigger when you pull them. It's like counterintuitive. Anyway, by using that pattern, we're able to somewhat control the slumping process to get into things that were not symmetric or make them slump faster than others. And it gave us the opportunity to open up that cavity on the inside. So, okay, what's next? I have one more thing to show you after this, but I wanted to do some acknowledgments. The Design Museum, of course, thank you. Ashley Lukasik and her company Murmuring, thank you. Studio Sato, Jessica did the printing of those little white things, the little white flyers. If you see them, they're beautiful. Elizabeth Terrett works with me a lot. She helps with a lot of the simulations. Anna Meek designed the book. So if you haven't had a chance, you can take a look at it. It is really beautiful. I treated it more like an art object than anything. Some of the images, 3form light art, Electric Garden, my collaborator Misha for the book project, Katie and Wes, and then Guardian Glass funded the glass project. So the last thing I want to show you is a little bit, this is not in the essay. This is one of those neat time-bending things you can do with simulations. In fact, we're going to make time stand still. So usually I take that ticker off of the top to show these simulations. But in this, so remember in the simulations you've seen so far, we determine a geometry, whatever that is, we let the sound go. In this case, what we did was determine a geometry, let the sound go, and then tweak the geometry a little and do it again, and tweak the geometry a little and do it again. And then we went in and grabbed a single still from each of those at exactly the same point in time. And it was at almost 1/10 of a second. So what you're gonna watch is the way the sound field looks inside of an enclosure at an identical time, not moving, but as the boundary changes. And what to watch for is that when the boundary is like this, it's actually fairly well distributed. As the boundary changes, you will see it get less and less well distributed. Eventually, we'll arrive at the circle. So go ahead and play it. And that's the still we grabbed it at. And to say a couple of final words, I realized that I was potentially asking for trouble in calling the essay Acoustic Ornament. Ornament is one of these things that is really troublesome sometimes in the design world because there's a lot of talk about what its function is, if anything. And it occurred to me that with sound, there's this interesting function that's always been there. In that if the ornament, if it's not two-dimensional ornament, if it's not just visual, if it's three-dimensional, it always changes the shape of a space and therefore always changes the way that it sounds. And it's not a coincidence that as the ornament went away, as modern design rose up, we started to get more and more reverberation, and that's also when the acoustic product industry rose up. And they were the ones who were like, hey, people want to design in a very minimal way. We need to design things that they can reach for to offset that. And I think that's an excellent option to have. And I'm not necessarily an advocate for ornament, but I do think that this awareness, I think, opens up a lot of possibilities and might resolve some of those issues that the ornament has had.